Hi and welcome back to Podcast School. This is an A2 Technology and Design video podcast. We follow the SIA syllabus, that's a syllabus from Northern Ireland, and we're looking at Unit 3.7 of that syllabus. If you actually want to download the syllabus, you can from the website, from the Podcast School website. Today we're going to look at Boolean Algebraic Identities, and this is part 1, so there's a clue. There is also a part 2 coming up. But for now, part 1. Okay, so let's get a few things straight. We need to know what an identity is. And I've said there that in mathematics an identity is a statement true for all possible values of its variable or variables. Let's say that we take an identity that tells us that anything, let's call that A, added to 0 equals the original anything, no matter what value that anything may be. Okay, so A plus 0 is always going to equal A. Let's replace A with a 5. 5 plus 0 equals 5. It's a rule, in fact, and it's always true no matter what. We've known this for a very long time. So that's an identity, an example of an identity. The OR gate, and we saw earlier in the last video podcast that whenever we use an addition sign, that has something to do with OR gate. So additions think ORs, they map. So if we have an A and a 0 as inputs, if we keep one of the inputs, let's say the lower one at 0, and use A as the upper input, well, if A were a 0, the output would be a 0. So there again, the output matches the input. It has this identity, it keeps this bit true. If A were a 1 and we add a 0 or with a 0, that gives us a 1. So again, the OR gate keeps this identity true. You can see that again from the circuit diagram. I like these circuit diagrams because it puts everything back into the real world. With this lower switch being open and A being either open or closed, it doesn't matter what 0 or what the switch does. If A is closed, then the LED will light, but if it's not, then it won't. Okay? I've said there, no matter what the value of A, the output will always be the same. When A is a 1, the output will also be a 1, and when A is 0, the output will also be a 0. But the important thing here is to remember this identity. A ORed with 0 equals A. Notice I said ORed and not added to. The next identity is most definitely different from normal algebra. Okay, I've said that A plus 1 equals 1. Now that won't make sense in the real numbers world, will it? But if we have a look at our OR gate here, and remember ORs come with addition or map with addition. So A ORed with a 1 gives us a 1, no matter what. Because no matter what A is, if we have a 1 in the lower input, it will always be a 1. We know that from our truth tables from before. Again, if you look at the circuit diagram, if this lower switch is closed, it does not matter what A is at all. It'll always light the LED, or in other words, it'll always be a 1 at the output. Okay, no matter what the value of A, the sum of A and 1 will always be 1. So that's our second identity. Now, what happens if we add A and A together? So for this, I've used the OR gate from before. Remember, adding is OR gates. I've got an A in the input, and we're adding it to another A. We're ORing it with another A. So the simplest way to do that is just to connect the inputs. So what am I going to get at the output? Can you think? Well, if A were a 0, that must mean that both inputs would be a 0, therefore our output would be 0. If A were a 1, then both inputs here would be a 1, and again our output would be a 1. So I think you'll agree that A ORed with an A must equal an A. It's the same. And there you have the identity. Okay, that's our third identity for addition. So I've said there, in real number algebra, the sum of two identical variables is twice the original variable's value. X plus x would normally equal 2x. But remember, there is no concept of a 2 in the world of Boolean maths, only 1s and 0s, so we cannot say that a plus a equals 2a. Thus, when we add a Boolean quantity to itself, the sum is equal to the original quantity. So 0 plus 0, or 0 or 0 equals 0, and 1 or 1 equals 1. But both of those are fulfilled by this identity, a or a equals a. Okay? So these are the facts so far. We know that a ORed with a 1 gives us a 1. And we also know that a or a bar, and remember a bar is the complement of a, equals 1. Okay? So by using and by putting both of those together, we can deduce that a ORed with a bar must equal 1. So if imagine, for example, a were a 0, then a bar would have to be a 1. And we know that if anything ORed with a 1 gives us a 1. If a were a 0, on the other hand, well then a bar would be a 1. Maybe that's what I said the first time. I can't remember. But you know what I mean. If it's swapped round, let's say a was a 1, then a bar would be a 0. But still, 1 ORed with a 0 gives us a 1. So this identity is quite important. And we can see that the logic equivalent of that is this circuit. We have an inverter here. We have an A as our single input, going straight through to the top input, but in the lower we have it complemented, and the output is always a 1. Okay, and there's our circuit diagram. So that gives us 4 identities for Boolean addition or ORing. Okay, in the next video podcast we'll look at 4 Boolean identities for multiplication or the AND function. But that's for next time. Until then, bye bye.